Hello, everybody. My name is Anton Hinneck, and I'm a PhD student with the Center for Energy Science and Technology at the Skolkovo Institute of Science and Technology in Moscow, Russia. I would now like to present our conference contribution, which is titled Optimal Power Flow with Substation Reconfiguration. Introducing the structure of this talk, first, I would like to discuss the motivation of our research. Then I want to introduce the method devised by my colleagues and me, introduce some computational results, and conclude with a short summary and directions for future research. Switching operations and optimal power flow models have already been subject to extensive research, and previous results have shown that such switching operations can remove congestion, improve the economic dispatch, and increase operational security. Challenges with regards to such methods are the increased computational complexity due to the combinatorial nature of such problems, and non-continuous changes in a system's operating point when switching actions are performed, which raises reliability security concerns. And these non-continuous changes can also be observed with respect to dual values, for example, which then has market implications. Switching frameworks are distinguished by the degree of topological control that they facilitate, whereas optimal transmission switching only allows for transmission lines to be switched on or off. Optimal bus splitting or substation reconfiguration allows for more profound changes of the topology. Optimal bus splitting would furthermore accurately classify the method that we are proposing in this contribution. Looking at reference 4 specifically in table 1, we can see that mixed integer programs that allow for optimal bus splitting have already been proposed. However, to the best of our knowledge, no general method has been devised that would allow for general bus substations to be modeled. And of arbitrary design and layout. Furthermore, we haven't really seen comparative studies that would compare different switching frameworks with respect to their objective values that can be achieved, which are basically the major challenges that we would like to tackle with this work. Now I want to present the method that we developed, and it basically requires 2 major steps. Given the model of an electricity network, this would be your standard test case. We must construct a substation representation for every bus V in that original network. This is illustrated in figure 1. You have an original bus on the left-hand side, and then on the right-hand side, the substation representation. Using this augmented network data, we then solve a mixed integer program and can then afterwards, after obtaining a result, reduce this augmented network to something that looks a little bit more again like the initial network, but preserves the switching actions that we've made. The substation representation is constructed as follows. A bus, like any substation, connects different components like generators, loads, and lines. And for each of these components, we create a new auxiliary bus. Furthermore, the user must decide on the amount of bus bar segments in a substation, which could be any integer greater than 0. And again, based on this information, auxiliary buses are created. Then we must run additional procedures to, for example, relocate lines, because a line that is connected to an original bus V now must be created to an auxiliary bus in our substation representation, for example. And then phase angles theta must actually be equal for all the auxiliary buses in a substation representation due to various reasons, but this is then addressed in the formulation directly. Secondly, we then create auxiliary lines that connect all the newly created auxiliary buses. These are switchable and don't have any electrical properties. This is necessary because otherwise we would change the electrical properties of our initial network, which we don't want to do. And furthermore, we must prohibit the formation of cycles in our substation representations. Otherwise, we obtain a degenerate problem, will not obtain well-formed solutions. But again, this is something that we can address in our formulation that I'm going to discuss now. There's only a few things to point out here. First of all, we're looking at basic DC-OPF constraints because this is the fundamental model that we use. Constraints 4, 5, 6, and 10 basically facilitate switching actions of our auxiliary lines in our substation representations, and then constraints 11 actually prohibit the formation of cycles. Constructing substation representations and solving the mixed integer program, like I've discussed on the previous slides, has some very useful properties that are outlined graphically on the slide. So first of all, comparing our method to standard DC-OPF, we can actually recover the standard DC-OPF if we only create one busbar in our substation representation and constrain all of our switching variables for each auxiliary line such that every line is switched into operation that is connected to that very first busbar. Secondly, if we relax this model a little bit and make all the lines switchable that connect feeders to our distinct single busbar, we actually recover optimal transmission switching, as has been mentioned previously. And we therefore conclude that these two problems actually, the optimal solution to these problems are actually upper bounds to the solution of our problem, of the optimal bus splitting problem as we formulated it. And we can also conclude that computing solutions for optimal transmission switching, which is a lower cost formulation, actually allows us to transfer such solutions to our method, import these solutions into our method and use them to tackle more challenging problems. Applying the method that I have described to the PGM5 bus case results produces the result that is visualized in 5A, and based on the optimal solution, which also includes switching statuses of all the auxiliary lines, you can now see that in substation 1, for example, we have two independent circuits. Auxiliary bus 6, 10, 11, and 12 are connected to one another, but are independent of auxiliary buses 7, 9, and 8. And if we now reduce this augmented network, preserving this solution and comparing it to the optimal topology we would obtain using optimal transmission switching, we can see that optimal transmission switching results in line 5 being non-operational, and optimal bus splitting results in bus 1 and 4 being split. We can also observe that the objective value actually for optimal bus splitting is lower, and we get a better solution. And this is something that we wanted to confirm on a larger array of test cases, which is summarized in table 3 right here. So there's a few things to note. First of all, and this is not really a surprise, our bus splitting formulation is more complex, simply judging by the amount of binary variables. We have a binary variable for every auxiliary line. And for the 118 bus case, for example, we already have almost 10 times as much binary variables than with transmission switching alone. However, we can also conclude that the improvements in the objective value can be significant. We can improve the objective value over optimal transmission switching just by finding better topologies by almost up to 20%, which is significant. And yes, lastly, all of our test cases were stressed so that we would actually be able to obtain improvements, because for non-stressed systems, usually no improvements can be obtained with topology control. So concluding this work, higher degree of topological control results in better solutions. The increase in computational complexity actually yields, and this is very important, tractable problems. So even though we increase computational complexity, we're still able to find solutions. However, we also saw that a lot of the optimal solutions tend to be radial for all the networks that we considered, and therefore future work will focus on security criteria and employing advanced computational methods. Thank you very much for your attention. If you have any questions, I would be glad to answer them. Thank you very much.